Okay, question number 9, the penultimate question, was all about probability. And we've got a situation where 2 dice have been rolled, and we're interested in the score of the total of the 2 dice. So x is this, it's a random variable. What's the probability of getting a 6? Well, if it's the sum, then the ones we're interested in are these outcomes. Probability of x equaling 6, there are 5 of those and 36 outcomes overall. What's the probability of getting greater than 6? I'm not going to ring all of them, but it's all of these. Count them up: 1, 2, 3, 4, 5, 6, 7, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21 over 36. If you're feeling really clever, you can divide by 3 to get 7 over 12. Now, find the probability of x equals 7 given x is greater than 6. Now, this is a conditional probability question, so straight away go through the formula. The probability of this, what they're wanting, is equal to the probability of x equaling 7 and probability and x being greater than 6 divided by the probability that x is greater than 6. And an algebraic version of this formula is in your formula booklet. Now the trick is, we can't just multiply these 2 probabilities. We need to think logically about it. Now the probability of x equaling 7 and x being greater than 6 is just the probability of x equaling 7, because 7 is greater than 6. So actually this can be reduced to the probability of x equals 7 divided by the probability that x is greater than 6. Go back to our table. How many 7s are there? 1, 2, 3, 4, 5, 6. 6 over 36. And what's the probability of getting greater than 6? Well, that's what we had in our part 2 answer, and it was 21 over 36. Notice how I've gone back to the unsimplified version, because now we can just cancel out the 36's. We're left with 6 over 21, which is 2 over 7. Not an easy question. 2 parts to it. First off, here, where we have to use the conditional probability formula, and secondly was noting that it wasn't just a simple case of multiplying 2 probabilities, but actually anything which had x being equal to 7 would necessarily have x being greater than 6. Okay, moving on. Part B, Elena plays a game where she tosses 2 dice. If the sum is 6, she wins 3 points. If the sum is greater than 6, she wins 1 point. And if the sum is less than 6, she loses k points. Find the value of k for which the game is fair. For it to be fair, then we're saying that e of, and we'll call it y because x has already been used, e of y is equal to 0. So our expectation, or our mean, is fair, i.e. we think we will get as many points lost as we will win. The expectation is equal to each score, or we'll call them score y times by the probability of x of y equaling that score. Well, in this case, she can get 3 points if the sum is exactly 6. So 3 times the probability of getting 6. Well, that was in part 1. The probability is 5 over 36. Plus 1 point times by the probability that the sum is greater than 6. Well, that was our answer here, 21 over 36. And then if the sum is less than 6, she loses k points. Well, that means our score there would be minus k, and if it's less than 6, well, let's go back to our table because we haven't worked that out yet, but less than 6 would be all of these in black: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Times by 10 over 36. Put that all into one fraction, and notice that I've used 36 each time because that will make it easier to put it into a fraction, and we get 15 plus 21 minus 10k all over 36, and for it to be fair, then that has to be equal to 0. Simplify the top, we get 36 minus 10k over 36 equals 0. But if this fraction is equal to 0, it's not the denominator that makes a difference, it's the numerator which makes a difference. So actually that means that 36 minus 10k is equal to 0, 36 equals 10k, and k is equal to 36 on 10, or if you like decimals, 3.6.